huge variation of people. And so that was the setup, and we went and looked around for different volunteers across campus. 4 male, 6 female, sit down, let's have a, get to know each other and have a conversation. And what we wanted to do was collect 3 different kinds of information from the interaction. One is the audio recording of the interaction, so we had a mobile phone recording the conversation. The second thing that we wanted to capture was their physiology. So their heart rate, their movements, and what we ended up doing was we actually ended up with, we were using a research-grade wearable from Samsung, SimBand, which had, I think, over 7 different kinds of sensors on it. So it was collecting information on blood flow, had PG sensors on it, had accelerometers on, a gyroscope to follow people's movement and gestures. It also took recordings on individual skin temperature and as well as the resistance of their skin, so like a light detector kind of sensor on the watch. And the third piece of information was the actual content of the conversation. So the audio contains information not just on the words that were used, but how they express themselves, so pitch, speaking rate, things like that. But we also were interested on the actual content of that conversation. So we had that audio transcript as well. So the 3 modalities is a summary: physiology from a smartwatch, audio recording from a smartphone, and the transcript of the content of the audio of the conversation transcript. And so what we were interested in evaluating was overall, was that conversation or that story a happier sound? And so what we did was, given all the different kinds of data that we collected, put a list of them here, we ended up with over 500 features. And I'm not trying to be a computer scientist, but it's
basically... Can we get a show of hands, actually? How many people are computer scientists in the room? Okay, got it, 1. So these features are basically just aspects like Tuka described, like temperature of your skin, the pitch in your voice, how many times was a smiley face, used in your message, stuff like that, right? They're just things that are meant to very concretely describe something about the interaction between those 2 people. That's all we mean by features. So we took those interactions, and we have a list of 500, like you can imagine an Excel sheet. For each person, we have 500 numbers, and we're filling in a number that describes 500 attributes of each conversation. Does that make sense?
And you can also think of it as, like, if you were trying to figure out whether someone's happy or sad, what kind of information would you be looking at? Would you look at the way they moved? Would you look at the kind of words they used? And so you could imagine sitting down with, and trying to write out what are the different pieces of information you'd be paying attention to. One advantage of doing this in a computational way is that you can actually have a very large and broad search space, not limited by how fast a human can pick up different features. So, with that, given that there are 500 still, it's a lot to work with. And it's a lot to work with for 2 reasons. One is, if I at the end of the day wanted to tell you, these are the top 10 things you should look at, it's very hard, or these are the features to look at, it's very hard for you to digest 500 features. But it's pretty straight, it's a lot more manageable to think through, like, say, 10 features, or 10 most predictive features of happier sound. The other reason, and it's a technical reason why we wouldn't want to work with all the features, is because if you don't have enough examples, you need many more examples or subjects relative to the number of features you have. So there's a technical limitation there. And so we want to use the most important features, and there's I would say, a straightforward way to do this, and in the machine learning computer science world, it's feature selection, and this particular one is a forward feature selection. There are many other techniques that could be used, and it's pretty straightforward. You start off all the 500 features that you're working with, and you have a model, an outcome you're interested in predicting is whether the conversation was a happy or sad, or the individual is happy or sad.
And I want to add here, because maybe some people in the room are not familiar with machine learning approaches. All that gray in the middle does is it takes something in the input and it produces a number between 0 and 1, where 1 is happy, 0 is sad. So it tries to take what you put into it and figure out where between perfectly happy and a perfectly happy conversation and a perfectly sad conversation did the person fall. That's what the box in the middle does, given what you provide. Go ahead.
So what you do is you say, okay, let me get my first feature, give it to that black box in the middle that's doing its magic, and it says, okay, like this feature 70% of the time it's correct in predicting happy or sad. So okay, that's the first feature. Then you take your second feature, and you say, okay, how well does this do? 60% of the time, it's right. And then you cycle through all your features, and you find out, oh, this one's 90% of the time correct at predicting.
I'm sorry, I just had a question. So, is this meant to assist it whenever it's determining whether it's happy or sad? Like if it says 90% of the time, is it you going in and assisting whether it determines a positive or negative response?
Yeah, so the black box in the middle is given some examples, and it's told, like, you have to learn the pattern here, that these, with these numbers, it's a happy outcome, with these numbers, it's a sad outcome. And then there's some hidden data, it doesn't know what the outcome is, and it's evaluated on that hidden data. And then you cycle through the feature. That's a really good question, because like people in the machine learning community tend to
Like assisted and
yeah.
unassisted.
So you cycle through the features. This next one is 80% of the time correct, and then you continue until you have your list of I guess performance for each feature.
Did you all have like a pre-selection for a fast pitch means sad, slow pitch means like I don't know, like
That's a fantastic question. So the hope was that we would be able to learn. So what you're saying is actually very smart. You're saying, okay, it makes sense that if I'm speaking really, really fast, right, I'm probably more excited than if I'm monotonously sitting here and delivering a presentation like this. Yeah, there's going to be a difference in whether someone's probably excited or not excited. And you're saying, oh, I can incorporate that information in the model. What machine learning is supposed to do is figure that all out automatically. You give it a little bit of constraints and some data, and it's supposed to figure out those relationships. And in fact, Tuka will show you some of what you're predicting is going to show up later. Yeah.
So, once we cycle through the features, we say, okay, like this, let's say, this temperature, skin temperature, that seems to be the most predictive feature, the outcome that we're looking for, which is happy and sad. So we keep that in the model. We say, okay, we're going to keep this feature. And now let's cycle through the rest of the features, given that we have this first feature. So this black box now is working with two features, but it's evaluating the second one iteratively. And it goes through all of them and says, okay, we found this particular feature, let's say it's accelerometer. It performed the best given this first feature. And so now we keep that in our bundle of features or bag of features that we work with. And then once that's done, we cycle through and we end up with the top 10 most predictive features of the outcome that we're interested in, which is happy or sad. And what those features look like.
Oh, she had a question. Go ahead.
In the models, what is the threshold in determining which feature stays or goes? Is it that 90%, like, oh yeah, it does really well at this level, so we'll continue, and it predicts like you get an R-square value or something at the end? I don't know.
Yeah. No, great question. So when you're doing a standard linear regression, which I'm assuming, so does everybody, you can see show of hands, does everybody know what linear regression is? Okay, good. So the difference between a linear and a logistic regression, which is the model here, is imagine, so the problem with a line is you can't map that to a probability easily, right? Because, the line just keeps going for infinity. So what you want to do is you want to grab the line and you want to just bend it so that it saturates at 1 and, caps at 0. So if you shove a regular line through a sigmoid, the sigmoid transform is 1 over 1 plus e to the power of minus, and then a linear equation. That sigmoid basically takes the two ends of the lines and bends them so that it's between 0 and 1.
Yeah.
So when you do that, that way, the relationship between the features and the outcome are constrained such that you never get an outcome that exceeds 0 or 1. So that was the first subtlety I wanted to make clear about when you're using a logistic regression. The second thing, to answer your question directly, which was about how do you choose the threshold of this, right? That was the question. Okay, so what you really want to do is, let's think if we were designing an experiment and we wanted to make one of these really work. What we do is we would take some people in this room and we would train that model using, let's say, 80% of the people in this room. And then what we would do is we'd say, well, for the 20% that we, or the 10%, let's say, that we held out in some case, and there's still 10 that are left in the corner, let's grab another 10%. We're going to look at these guys and say, how on that set did these features do in predicting them? And if it does really well there, then we say it generalized. Otherwise, it could just be that, they have this thing called overfitting, for those of you who have heard of it. So you always test on a set that you've never looked at. If you start getting improvements on that set, that's when you don't keep it. But if you don't get an improvement on these group that you had never trained the model on or looked at, then you throw it out. You don't add anymore. Does that answer your question?
Yeah, totally. Thank you.
You're welcome.
Okay, so we ended up with 10 features, and we plotted them according to the model coefficient. So the weight in terms of how strongly a particular feature predicts a happy conversation or a sad conversation. So on the left side, you have features which most strongly predict a positive or a happy narration, and as you go towards the right, you have features that are predicting negative narrations.
And if I may jump in, so that some of these are not clear, I mean the labels are not immediately obvious. So that PPG sensor, you see how that shows up in 2 places? That's the posture when you're having the conversation. This versus this. Like, are you kind of like, your posture depends, that's what the PPG sensor tells you. So what it tells you is, as you were pointing out, okay, it makes sense. If I wanted to catch a happy or sad conversation, there should be something there. What's interesting about this is it learned it on its own. Right, completely on its own. It figured out that this kind of posture is a bad sign and this kind of posture is a good one for a conversation.
I think my question, and it kind of goes to maybe a more in-depth explanation. I don't know if it's coming up forward, but do you assign what does being sad, what values does being sad mean versus what values does being happy means, or does the machine just group all these values assigned for all these factors, features assigned for a value near 0, and all these features assigned for a value near 1, and then you just make the conclusion? Is that like that, or do I have a wrong idea?
Well, could you clarify? So, are you interested in how formally the model is trained, or? Yeah,
basically. So, how can you assign data for the posture like this to be equal to 0, or like close to 0? Because the data will just be numbers essentially.
Yeah, for sure. So I'll actually show you exactly how you do it. Okay, so formally, the process that you're trying to solve here, the process you're trying to solve is this. You have, so you guys know what the simple linear equation is. You have a y is equal to an mx plus b, right? This is the standard linear equation, so it says this. I have an intercept b, and then I have some slope called m, and I get a line like this. And it draws a relationship between, let's say this is the posture. So the posture is it's a signal, right? The signal is, let's say it's a voltage. It's some number between, minus infinity and infinity. It has some range, of course, right? But let's say it's between, minus 50 and 50. So it's in this range here, okay? So here's what ends up happening. As we mentioned before, you want to predict a y here, which is a probability of associated with 1 is you're perfectly happy, 0 is you're miserable, you're not having a good time. So what we're going to do is we're going to take this equation, y equals mx plus b, and to bend this line both ways, you shove it through a sigmoidal transform. So that is precisely just this. So 1 over 1 plus e, and then you take this and you stick it there. When you jam that through this thing, it bends the ends of the line. And this ends up becoming like this. So that it does this, right? And this doesn't exceed 1 then. Okay? So now what you do is, okay, you want to train this. So here's the way formally the training happens. So I have some data points, I have some values of x, right? And I know what the corresponding outcome was. I have a y. So let's say that for one subject, this y was, he had a happy conversation, so it was 1. And let's say the x value was something that was very low. It was, 0.2, okay, or close to 0. So I'll draw them here. So let's erase this and just draw the relationship again. So if I saw that every time, the x value here, the value of the signal, as it grows, I'm getting more and more zeros, like this, and only a few ones. Let's say it looks like this. And then let's say that as it gets further this way, I'm getting more and more ones, and a couple zeros. So what would I say? I would say, oh, the line is sort of like that, right? If I have to clip it between 1 and 0. So now what I have is I say, okay, as a function of what value of x I have, I can generate a probability of y. You see that? Does that make sense? Is it crystal clear?
Yeah.
Okay, great.